Well, now we start to introduce the Lagrange multiply method. Well, we know it's all pretty much completed all the single variable calculus. In here we call it calculus 1, the calculus 2 for single variable differentiation and the integration. But the Lagrange and took the position after Euler became the director of Berlin Academy in Germany in the 18th century. Well, that position is nowadays you can think about like in Princeton, the physical science lab. And what he's contributed most is the multivariable calculus and the optimization. That's what we are talking about in this lesson and the next lesson, the Lagrange method. So the problem he considered, we could put in a simple way. We got an objective function. That is the function f x y. You try to maximum and minimum under a constraint equation. So if you think about a 2D, I can do an illustration. Let me get another page. Okay. In 2D, a constraint is nothing more than a curve. And then along the curve, you figure out the f x y. Now, give you an example. If the G is this curve, you know it's a straight circle. And if you are on the circle, you try to figure out what is the f x y equals, let's say, 2xy. And then you move along the circle. See, that's 0, that's 0. And somewhere here, you might find this 2xy maximized, square root of 2 over 2, and times 2, that will be 1. And 0 here, 0 here. That's kind of question. So how do you know it's this point? And maybe this point, maybe this point, this point. How do you know here is not good? Well, you look at this x equals 0, y equals 1, you multiply equals 0, so it's here. This is 1, 0, it's also 0. Let me give you a simple idea of proof how Lagrange proof if that's the point P. On the curve gxy, maximize your fxyz, and all you need to give is this gradient must be parallel to that gradient g. I can give you a quick illustration, the proof. So I can write this gxy as a parametric equation. Say the x equal xt and the y equal yt. That we call it a parametric equation. For example, if I have a circle, I can write the circle as x equal cosine t, y equal sine t. And if we add the x squared to y squared, the Pythagorean theorem gives you what? Cosine squared plus sine squared equal 1. So in here, I have the gxt yt equal 0. So you move along this curve, you want to find the fxt yt be either maximum or minimum. let's take a derivative by the chain rule. If I want to take this derivative to g to t, see, right hand is 0, take a derivative to the left hand, it's supposed to be 0. By the chain rule, you get this. I do not know if you connect all the calculus now. And dy dt equals 0. That's the chain rule. So your g equals xy t. That's how you figure out the derivative. Well, if I rewrite it, I will let this r prime, that's the derivative. Last time I told you is the tangent line direction. That's the tangent line. That's the r prime t. And then you can rewrite this as the gradient of g. See, the gradient of g is delta x, delta t, delta y, delta t, delta x. No, I'm sorry. The gradient is delta g, delta x, delta g, delta y. That this equals 0. In geometry, what does that mean? That simply means here you go, that's your gradient direction. And this is the tangent direction. Dot product equals 0, you know it's perpendicular. Well, you do the same thing to the f. What it says for the maximum minimum, you need the derivative equals 0. This now is a one variable function, and then this f prime t need to be 0. But the same chain rule, you get the gradient of f dot, the same derivative need to be 0. That's by the chain rule. So what I'm saying is, oh, this gradient at the point also need to be perpendicular to this line, which is the tangent line. So if two vectors both need to be perpendicular to the tangent line, these two lines has no other choice but the parallel. And when I say parallel, that's how I say the parallel. And they're only different by a constant lambda. And this lambda has a big name. What is this big name? Oops. And this lambda is called the Lagrange multiply. That's the lambda. So what we get is the gradient of f must equal the gradient of g. And then if x, y is two variable, I get two equations. So the delta f, delta x equals lambda delta g, delta x, that's one equation here. And delta f, delta y equal lambda delta g, delta y, that's the second equation. This is the third equation. How many variables we have? We got x, y, and the lambda, 3 variables. And the 3 variable and the 3 equations give you an algebraic solution. Those solutions will be called the candidate. The critical points could be give you the maximum and the minimum. And then we learned the sufficient condition if we really wanted to look if it's a maximum or minimum by looking at the determinant, which is the determinant of the Hessian matrix. And then you can figure out the maximum and the minimum.